Scoring and information. Information makes sense of scoring. Scoring is often stated in terms of information. Now let's compare again information and probability. Probability is based on counting. Information, we'll find out, is based on the average number of times that patterns of a certain type occur in trials for very large N. So information is well suited for applications involving big data, and information is the unifying theme for this course. I'll repeat that. Information is what we'll be seeing from now on, and that ties everything we've been doing together into one coherent set of ideas. Now let's recall our information entropy theorem is that if a random process occurs and produces m outcomes with probabilities p1 up to pm respectively for those outcomes, and if x is a variable associated with that process, then the Shannon entropy is h of x, which is the sum of the p of x, I of x, which is the negative sum 1 to m, the probability times the log base 2 of the probability, and the self-information here is the negative log base 2 of the probability, the self-information or surprisal due to the outcome x occurring. A nice way of illustrating these ideas is to use what are called multisets. So these are unordered collections which can include repetitions. So if probability of heads is a fourth, then we can think of that as tails, 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 heads. Everything works the same, including the balanced tree algorithm, and we're not being rigorous here. We're just going to use multisets to illustrate concepts for unequally likely events. So last time we had a spinner example where the probability of 1, 2, and 3 was a fourth, and a half, and we encoded that in the following way. We need 2 decisions to separate the 0 and the 1, but we only need 1 decision to get both 3's. So therefore 1 and 2 are encoded with 2 bits, whereas 3 only requires 1. So therefore we have d equals 4, since the probability of the 3 is a half, which is 2/4. So that's our denominator here, and so that means we can encode everything into log base 2 of d, which is 2 bits. And so the self-information from 1 and 2 is 2 bits. But the self-information for 3 is going to be less because 3 is repeated. So in particular, we're going to take the 2 bits and we're going to subtract the information due to the repetition, and that means the information from the spinner result 3 is just 1 bit. So surprisal, we have I sub 2 and I sub 1 are 2 bits, but I sub 3 is less surprising, it's just 1 bit. Now if we did n trials of the spinner, then we're going to get 1's occurring about n over 4 times, and 2's occurring about n over 4 times, but 3 is occurring half the time. We put that in and get the entropy by just taking the average, the frequency weighted average of these informations, and we get a fourth times 2, a fourth times 2 plus a half times 1, and that's 3/2 bits. So the average information from this spinner is 3/2 bits. So what do we have so far? Well, that example showed us that entropy is average information, and it can be expressed in many different ways, and the h of x is the average over all possible values of x, and I of x is the information due to x having a value specifically of some index x. So h of x, as you can see, it's a summation over all x's in all 4 of those representations, whereas the self-information is restricted only to a specific value of x. Now what if we had a zero probability? Well, if we took the limit as p goes to 0 of p log base 2 of p, then using L'Hopital's rule we can show that's equal to 0. So if p sub j is 0, then we can just set p sub j log base 2 p sub j equal to 0. Or in reality, the rigorous definition is that the Shannon entropy is defined as the average only over events with non-zero probabilities. Now let's look at entropy and independence. And we are going somewhere with this, but let's just keep going for right now with these observations. So if x and y are independent variables, then the average information, or the entropy, is the double sum over x and y of the self-information x and y. But because of independence, we can write the joint information I of xy as the sum of the individual informations. But that means we can write these two sums separately, splitting at the plus sign between the I of x and I of y. And notice that the sum over the y's is going to be a marginal probability. The sum over the x's is going to be a marginal probability. In particular, the first one is the marginal probability for x, and the second the marginal probability for y, but that gives us the sum of the entropies, the average entropies over all possible x and y values. So if x and y are independent, then their joint entropy, h of x comma y, is the sum of their individual entropies. In general, we can show that h of xy is less than or equal to the sum with equality if and only if x and y are independent. But we won't need that often. We will, however, use what we just proved, which is the independent variables joint entropies is the sum of the individual entropies. And this generalizes to more than two variables. And notice this implies that the entropy of simultaneous independent trials is greater than an individual trial. So in other words, as we add more and more trials, the entropy tends to get larger and larger. Or let's put it exactly. Suppose we have x1 to xn are independent trials of the same experiment. So we would say that x1 and xn are identically independently distributed. But that would mean that the entropies are the same for all of these, and therefore the joint entropy of x1 to xn occurring simultaneously is n times h of one single trial. And what does that mean? Well, if n is very large, then that means the entropy is large. And notice that complex data has many independent variables, and so therefore it necessarily has high entropy. It's disordered. Whereas patterns, as we will see later, have low entropy. So complex data you can think of as a high entropy data set which has low entropy meaningful patterns within that set of data. So why are we using information? Well, we're leading up to this idea, what's called the principle of maximum entropy. And that is the best model to use is the one that allows the most uncertainty. So a probabilities distribution should assign a positive probability to every event not excluded by the given information. In other words, information drives the modeling. And the maximum entropy principle is related to independence. But in general, what it says is that the best model is the one that allows the highest possible entropy in that data. The most randomness, if you want to think of it that way. So suppose we just had two outcomes, probabilities p and 1 minus p. The entropy in this case would be negative p log 2 of p minus 1 minus p log base 2 of 1 minus p, because your only two probabilities are p and 1 minus p. And if you look at this as a function of p, it turns out that h is maximized when p is equal to a half. and there's an actual graph of the entropy as a function of the probability. And clearly, just by symmetry, you can see that it's got a maximum at a half. So that means a fair coin is the most random process with two outcomes. So when we are looking to model the flipping of a coin, we would want to allow the possibility that the coin is fair, and therefore we would want to allow the most random process, which is the entropy when p is equal to a half. Now there are important consequences for this. We'll use information and entropy because it can classify patterns. It can also tell us when there are no patterns. But we're going to be using probability as well. Why? Because probability is highly applicable. Conceptually, it's not as valuable as you might think, but as far as in applications, we use it all the time. The concept occurs often. So in lecture 3, we used it to classify unlabeled observations. If we have measures where the result of the measure is between 0 and 1, like clustering coefficient, then it makes sense to call it a probability and then talk about information. So that's an important point. Even when using the concept of probability, our true goal is information. So here we have our clustering coefficient example again. We said this was 33.3% probability of two neighbors of V being adjacent to each other. The clustering coefficient of this hub is certainly 0, and the clustering coefficient of this vertex V with a complete neighborhood is 1. So if we interpret that as a probability, then it would say the self-information is 1.5849 bits. So in other words, 1 trit, if you want to think of it that way. And so you would need 1 trit to encode all possible ways of selecting neighbors at random and checking to see if they're independent, adjacent. Now, this middle one is the hub, and the probability of finding a triangle is 0, and therefore the self-information is infinity. Now you might think that's sort of strange, but actually we can interpret it to be meaningful. And likewise, you might look and say, well, if you've got a complete neighborhood that takes 0 bits, how can you say that it takes 0 bits to encode something? But when you think about it, we would be infinitely surprised if we were to randomly choose an A and a B in this graph connected to this vertex V and find an edge between them. There isn't one, so we would be shocked if somehow somebody snuck one in some way. On the other hand, there's really no need to do any encoding here in this graph. The neighborhood's complete, so as soon as you pick two vertices, they're adjacent, so that's the only outcome. We don't really need to encode it, so we really only need 0 bits to encode all possible outcomes of choosing an A and a B. Now, one last idea, and that is we can actually do a deeper exploration of information using modern algebra and in particular group theory. Now, we're not going to do this. However, the concept is very useful. So notice that a complete graph is completely symmetric, and the self-information from a complete graph is 0. There are no surprises. So you pick two vertices and there's always an edge between them. So the key is that if you have any change in the symmetry, you're going to increase the entropy. So the complete graph is the completely symmetric, and as soon as you take away one edge, you have created a bias in some sense, and you have destroyed that pure total symmetry. So applying that to the question I asked last time, the most symmetric graph is a disjoint union of k sub n, because anything else has less symmetry. And the clustering coefficient of a graph is 1 only if it has full symmetry. We haven't proven that, but it turns out that it follows pretty easily. So therefore we can say that full symmetry implies clustering coefficient of the graph is 1, and otherwise as soon as you drop an edge you've lost symmetry, and therefore you have increased uncertainty or randomness, and that means that the entropy went up and the clustering coefficient of G can no longer be 1. So we'll use this concept just like I've done it, but we're not going to use it rigorously. So we can use it without necessarily proving a bunch of theorems about symmetry groups and their relationship to information. So looking ahead, what do we got coming up? Entropy allows us to search for patterns. We can measure average information from a collection of patterns, and we can measure the performance of an algorithm using entropy. Now, one thing we're going to look at over the next 2-3 weeks is in the real world, there are always going to be mistakes. We're never going to get things perfectly. There will be false positives and false negatives, and we'll need metrics to measure performance as well as other issues like one you've already looked at, overfitting, or are looking at now. And it's all of these things that are going to be derived or have some kind of relationship to this concept of information.